Testing, testing.
Use shortcuts in deep note.
Not that much. I actually don't develop in deep note. I test.
I feel like deep note changed. I can't code in deep note because the shortcut doesn't work. All my favorite shortcuts stop working.
They were working and now they stopped. They changed them, or?
I don't know. I think the shortcuts are just different.
Yeah, they're just different.
All my favorite shortcuts are not working.
I see. It's funny to hear Tomas Lozano Perez. He talked about when he was writing his thesis, Richard Stallman was writing Emacs, and they had the one time-shared computer, right? So it was like they had to log in for time. He'd get 2 hours to work on his thesis, and overnight, Stallman would come in and change all the key bindings. So every day, the key bindings were different. Very hard to write a thesis, he said. In the first 30 seconds of lecture, I become chalk colored. Part of me, as I was prepping for this, makes me, I think there's some simple simulation questions we could ask that are not in the piece set, but maybe I'll write some tonight for, and
You can do it for recapture the piece at 6. Or you
probably.
just add them to the set.
If I came up with if I had the energy to come up with something that got vetted tonight, then we could consider it for this week. Otherwise, I'll just do it for a future year, I think. But it does seem like we're going to have all our questions about Thursday and lots of cool stuff today, but no questions about it. The one I'm going to use an example in the first part here that I think could have been a question instead maybe, but I figured I'd just do the example in lecture. Bode plots. I think people do really grab the slides. It's good. I see it on a handful of screens. So. All right, let's get started. So we're going to start the next sort of chunk of lectures. We just finished 3 lectures roughly about point clouds and geometric perception. So let me just start by reminding you from a big picture where we've been and where we're going next. So we started off with a lecture about hardware basics, just to get you up to speed, and the mechanics of simulating all of the pieces, including the control stack and the like. And then we just got our robot moving with some basic kinematics and Jacobian-based control. And we took a single object and moved it from point 1 to point B, the simplest version of pick and place. And then we complemented that with a handful of lectures now about the simplest sort of form of perception. If we needed to now find that object from the cameras, then we had some basic tools to do that. In the spirit of now spiraling out and increasing complexity, what we're going to try to do is bring that pipeline into more complex scenes now. In particular, where we had just taken one object and it was a known object. In the next 3 lectures, I'd like to think about a bunch of objects, a whole bin of objects, cluttered objects, and I'm going to try to reduce the assumption that we already knew everything about the object when we started. So we started off before, we had a perfect mesh model, let's say, or a point cloud model that we were going to find, and we want to think about techniques that don't make that strong assumption. In particular, we're still going to do, in the first pass of increasing that complexity, we'll still mostly just pick things up and set them down. And after the next round of complexity then will be known objects with deep perception, and then more contact-rich manipulation and forceful manipulation. So we'll keep increasing, but the jump for this section is more complex scenes with many objects and diverse objects. So this is roughly what we're going to build in the next 3 lectures. This was a project at TRI that I think other groups have certainly done similar things, but this was, let's see, it was motivated partly by wanting to do deep learning for perception and needing to generate a lot of training data for our deep learning systems, right? And so we wanted to have relevant images of bins with relevant objects in the real world. So we set up a system that would basically move objects back and forth all day long, okay? And then we would occasionally go and dump new objects in and take other objects out, and this thing would just do its thing all day long. But the pipeline behind that was actually interesting in and of itself. Is how do you build this robust system that can pick up all the objects, actually getting every one of those objects out, or even some strange objects that can be put in, and getting that to a level of performance where it would almost always move all of the objects, was a pretty interesting undertaking, and that's kind of what we'll pursue today. We're not going to do the super handle every corner case version, but we'll get the nominal situation working well. It was interesting, if you would walk by this robot, it would be operating all day. Every once in a while, there'd be something on the floor. Actually, there was at some point, someone threw in this rubber duck that looked like Spock from Star Trek, and for some reason, it always threw Spock. It was like with high probability, if you walk past for a couple days, Spock was on the floor. So it didn't like that. Okay, but this is what we're going to build. So that has lots of interesting questions, and we'll do it in 3 parts. But the first part is, how do you just generate those richer simulations? And how do you generate random kitchens or random distributions over what's going to be thrown in the kitchen sink or in a bin? Okay, and there's a pretty sophisticated answer to that could be trying to calibrate probability distributions over environments that we're not going to do in the first pass. We're going to do a simpler version of it first, but it's a super rich question. It's a big question for all types of, if I wanted to make a safety case for autonomous cars, right? How do I somehow write down a distribution of all the possible environments that the car could be operating in? What's the probability of a pedestrian coming in a certain way? It's slightly easier when you have inanimate objects, but still very, very hard to get the distributions of possible kitchens. So what we're actually going to do instead is basically drop things out of the sky. Here we go. It turns out, if you were going to go into the room and do something, you would just dump a bunch of objects in. And we have a really good simulator, which we're going to try to appreciate the details of today, because this is going to demand more from our simulation. But it turns out a fairly reasonable way to make cluttered scenes is to just drop a bunch of objects out of the sky, okay? And for reasons we'll understand by the end, it's hard to start it in this configuration. It's actually relatively easier to start it up in the air with the objects separated, so they're not in collision, and to drop them, and then just rely on an optimized collision engine that can simulate forward with high reliability, and then you get these interesting cluttered scenes, interesting distributions. I did this with many copies of the red brick, but the exact same code works for more interesting objects. I guess I don't know if I've explicitly said yet, but the mustard bottle, and even the red brick actually is in here, right? These are from a famous data set. There's my red brick, right? This was a project. It was Yale, Cal, Berkeley. There were research groups from all three of those that got together and said, let's make a common data set for robotics. And they picked a number of SKUs from Amazon. They would tell people how to buy the same objects. They would even ship you some of the objects. And they gave out 3D mesh models of these objects with high fidelity texture maps, like super high fidelity. I mean, well, maybe not fidelity, certainly high megabyte count, right? The reason it takes so long to load in MeshCAD is because these things are super enormous meshes. Okay, but it's been a very valuable, and you see lots and lots of manipulation research today still that uses these data sets.
I think C stands for CMU.
What did I say? I said Cal. I said Berkeley twice. Yeah, sorry. CMU Berkeley, thank you. That was Sid at CMU, yeah. And so you can do exactly the same thing. You can load those objects into the simulator, drop them from the sky, and get interesting distributions of YCB objects, okay? I love this because this looks like the central limit theorem, right? But it's got Spam cans and mustard bottles and all kinds of bizarre objects, right? So something kind of amuses me about that. Okay, but generating these scenes is going to allow us to do drop a bunch of objects in the bin, take a picture above, and then we'll be able to make ground truth labels for a deep learning perception system for next week, whenever we get to it. But the demands actually on simulating this well are increasing the demands on our physics engine. And so I think this is a good time to sort of stop and think about what's happening in the physics engine a little bit more. It's going to dust off some of your 1803 skills and feel a little bit like mechanics. So those of you that don't like mechanics will hopefully get a little refresher and appreciate some of the details. But it's another one of these. Hopefully there's levels of detail for different people in the class. Okay, so I have said before that simulation for manipulation actually has proven to be harder than simulating for other types of robotics. Certainly for quadrotors flying around in the open air, that doesn't have as complex physical interactions. I mean, you can get ground effect. You can start doing serious aerodynamic modeling, but vehicles have tended to be simpler to simulate, first things to simulate well. Walking robots are actually not so bad to simulate. We've done for many years, we've trusted our simulations. But it took a long time for us to actually believe that we could simulate the complexity of manipulation. And so why is that? It seems like walking robots should be just as hard to simulate. A walking robot doing a backflip should be just as hard to simulate as manipulation. Okay, so we're going to talk through that today. And there's a few major points that I want to make, right? So let's say simulating contact for manipulation in particular. Challenging. So the simulation, of course, means many things, but I'm talking about the physics engine piece of the simulation today, okay? And the first one is that we end up with stiff differential equations. Often. This is partly under your control, is how stiff these are. And that's one of the, I think, even just as a user of these simulations, understanding where stiffness comes from and how to deal with it will help you use these tools better and understand when things go wrong, what you can do to fix them. So let me take a few minutes to sort of explain what I mean by stiff differential equations and how they manifest in these kind of simulations. Okay? And I'll do it with I don't even need a big complicated walking robot or manipulation system to make this example. I can just even think about stiffness in a spring damper system. Okay, so let's just say I have a mass spring damper. This is really your 1803 type system, right? So let's say I've got just a mass. There's no friction to speak of, and I'm going to put a spring on it, and I'll put a damper on it, which we normally draw like that, okay? And this will be its x position Okay, and this is like x equals 0 here. Okay, so the equations of motion of this, actually, let me call it not x, let me call it q, since we are going to distinguish between x and q. And we've been calling positions q, right? So this is going to be mq double dot plus bq dot plus kq. This is the classical equations of a damped oscillator, right? Where this is the mass matrix, this is the damping, and this is the stiffness, spring stiffness. Okay, so in my other robotics course under actuated robotics, we talk a lot about stability and what that means and how to generalize it to nonlinear systems. But I think even without that full introduction, we can talk about just the basic stability of this system. Stability in this very simple setting is just asking, is the limit as time goes to infinity of x of t equal to 0, q of t, right? I'd like to say if I start this here with some initial position and velocity, and it starts ring, 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 is it going to come to rest, or is it going to do something different, right? This damper is the physical intuition you should have is that's pulling out energy, that's friction, right? So this thing wants to oscillate because of the spring, but it's going to slow down because of the damper, and we're going to try to make sure we understand how to simulate this accurately, even if you've got these kind of simple equations. Is that clear? For the continuous time system, the answer, the question about stability is very easy to understand. You could ask, what is the stability properties given I change m, b, and k, the parameters? And it turns out that the answer is yes, it's stable. I'll just say if mass is greater than 0, the damping is greater than 0, k is greater than 0. As long as all of my numbers are positive, which is the normal physical intuition case, then yes, that system is going to decay. And I put strictly greater than 0 for the damping so that it's actually decaying to 0 and that's not oscillating forever. And this just because I don't want mass to be 0, right? Okay, and if I wanted to if you remember your differential equations, right? So I obtained this with confidence by taking the eigenvalues of the system, right? So if I write this in my state space form, just to completely close the loop, here I've got q and velocity, q dot, and this q dot does equal v in this simple case. So I can write q dot equals, or x dot equals q dot, and then 1 over m negative b q dot minus k q, which I can write that as ax, where a is just 0, 1, negative k over m, negative b over m. Is that familiar to people? Give me a thumbs up or a thumbs down. Is that familiar to people? That kind of stuff? It's been a while maybe, but this would be a differential equation way to think about that system. I could just write the equations of motion in this form. This is, for this example, you don't need to generate these from scratch here, but for those of you that remember, then the eigenvalues of this matrix can check the stability of the system. Yeah. Okay, so what's interesting now is if I try to integrate that on a computer, right? So that you could take an entire course on numerical methods. I don't need all of that, but I just want to think about numerical integration in its simplest form here to make a few points. So this is a continuous time equation, And I want to now integrate it forward with an algorithm, right? So the simplest form of that would be to make an approximation here, a discrete time approximation, to say I'm going to advance this simulator by taking my current state, and I'm going to increment it by, I'll call it h. This is my dynamics. This is my x dot, right? This one here, h, is what I'll typically use to denote my time step. I want that to be also greater than 0. Okay. And if you care about the linear analysis, again, you could write this as I plus h a x n. This gives me a different linear dynamical system, which we can talk about its stability or its instability, asking does x of n, as n goes to infinity, does it go to 0? And nice questions from analysis are about, if I choose different h's, for instance, how accurately can I simulate the true solution from this differential equation? These are the fundamental questions of numerical analysis. Okay, and the answer here is much more subtle than this, right? And I think I actually have the eigenvalues here, but they're messier than I wanted. So I'll just do it numerically. I'll do an example numerically, okay? One of the great things about linear dynamical systems is I can integrate them perfectly in closed form. So I can give the solution to this with no artifacts from numerical integration. And then I can do the integration version of this and ask how similar they are. By the way, this is a particular type of integration. This is called the Euler integration. You've probably heard it. It's even forward Euler if you want to get more into the details. Okay, so I'm worried that this is not going to show up great on the monitor because WebGL doesn't accept the line width command. It's sort of annoying. But let's try. Oh, I could try Safari. I wonder if Safari's WebGL supports. Okay. Nope, still doesn't. Like right in the WebGL docs, it says most browsers don't support line width. So, okay, that's annoying, but we'll deal. This is the phase portrait. Let me draw it first on the board just to make sure you know what we're seeing here. I'm going to go in and add like axes and other matplotlib-like things into Meshcat, but I haven't done it yet. Okay, so the plot I want to make here to understand the integration of this mass spring damper system is a phase plot. Phase portrait, even. Which is when I plot Q versus Q dot. So if I plotted Q as a function of time, I would expect to see an oscillation that would decay if it's stable or blow up if it's unstable. But the timing of this is one feature, and I'm less worried about the timing. I want to see more its long-term behavior. It's going to be a little bit clearer to see it in this plot, where I'm going to start. If I start from some initial condition, let's say a positive Q and 0 velocity, then I would expect it to start getting pulled towards the origin. So that's negative velocity, and you'll expect, it's, I think, not too hard to see that we're going to expect something like that to happen when it's stable. When velocity is positive, I'll be moving in this direction in this picture, right? And when velocity is negative, I'm moving this direction. So I'm going to tend to take spirals, and in the good case, when there's damping, I expect those spirals to be like this. Okay, so that's what we're seeing here. We're seeing an initial condition here, and this is the origin, and I can change the stiffness and damping and the like, okay? And this is chosen with a pretty small h. H is chosen to be 0.1 seconds here. Okay, so I have a mass of 1, a damping of 1, which I should have picked 0.1 or something, and a stiffness of 2. So these are all kind of like around the number 1, I get this sort of reasonable solution. Interestingly, as I increase the stiffness, this is making k bigger, then I'm going to get elongated. I'm going to get larger velocities, right? I'm going to like this, right? But it'll still eventually converge. Now the red line, so the blue line is the analytical solution, no numerical integration accuracies. The red line is the numerical approximation that I get from doing Euler integration. Now the natural thing you could imagine is if I start taking bigger steps, right? So what it's basically doing is it's taking the derivative at each time and then forecasting that out as if it was constant. And then it's evaluating the derivative at that time, forecasting it out. So it's going to make an approximation of that curve. The problem is if I pick h to be, I'm going to start increasing h now. So if I start increasing h, my approximation is going to get more and more decimated, okay? And my accuracy is going to go down, right? If I increase h too much, okay, sorry, that was the stiffness. If I increase h too much, things can get bad, right? So I'm simulating a system that is, the continuous time dynamics are stable, but the discrete time approximation is unstable. This seems totally artificial and forced. You might see a simulator do this on you one day, okay? And it's the same, the reasons for it are exactly what we're seeing here, okay? So the very first lesson is just, if you see your simulator blow up, turn the time step down. That's the first one. But actually the interaction with the stiffness and the damping and the mass is actually easy to understand too, okay? And we're going to try to make sure that those points land. Okay, in particular, what matters is the time step as a ratio, or compared relative to the not k, but k over m, okay? So the thing that matters is h relative to k over m. These are the accelerations. This is like the q dot, the nominal q dot. I'm sorry, q double dot. Okay, this is the stiffness divided by masses. And if k over m is large, then you're going to need a smaller h to simulate it accurately. Because that's going to make, if I increase k here, if I increase k, that's getting my derivatives are going to be larger. And so taking a long step with fast changing derivatives can quickly lead to big errors. That's the intuition. If your accelerations are big, then you need to make your time steps small. So it turns out that when you're simulating a humanoid, let's say a 400-pound Atlas robot that's generating relatively big forces on the ground, you would think that might be a hard thing to simulate. But actually, the accelerations are relatively low. Okay? So big forces on a big robot are kind of okay. When Atlas goes to pick up like a toothpick, that's the bad case. You get big forces on a little mass, and you send toothpicks flying in your simulator. Okay? And it turns out EWAs picking up stuff are not so different from that. And in the range of inertias that you have to deal with in manipulation is the first challenge. You tend to have very stiff equations. And also, the accuracy of the contact simulation is such that you need to choose k larger than you would for walking. And I'll make that point when we get into the contact equations. Okay, does that basic idea make sense? What does it mean to be a stiff differential equation? It means that I have these accelerations, this k over m in this simple system, is large, which means k has to be small. I'm sorry, h has to be small. Good. So we're going to see now where some of that stiffness comes from in the contact problem. Let's do a little contact mechanics. I'm going to take almost the same example, but I'm going to put a contact inside it, okay? In fact, I'll do it in the vertical plane this time instead of the horizontal plane, just so I'm pulling down with mg, okay? And I've got a ground here, and I want to think about what happens if my point mass goes into the ground. Now, your physical intuition will probably tell you all kinds of things about that. First of all, you'd probably expect it to bounce, but that will depend on our contact parameters. Some of the models that we're going to talk about, it's actually going to go and stop. It depends if you assume that the ground and the point are infinitely rigid, then actually, unless you do something else to model restitution or something like this, then actually rigid contact would have it defined as just coming into losing all of its energy on collision. And so most of our models, most of our mathematical models are actually rigid geometries. So the default answer actually is stop. But we'll see ways to make that better. Okay, so this is almost the same equations, but I don't have damping now. I just have, if I call this now the z, and z double dot is just negative mg is when I'm in the air. But then once I get to the ground, I'm going to have a contact force. Let me call it the normal force for now, but we're going to use our full spatial notation after the basic example, okay? So when it's on the ground, I'll have this force of normal, and I'll have the mg, both. Okay, so then in this case, my equations look like this. Like I said, you might expect it to bounce, but we'll see the cases where it's not. So the question is, where does Fn come from? When it's at rest, you can sort of imagine that Fn will be negative mg, and you'll have an equilibrium. But it's more interesting to ask what happens when you collide. Okay. So option 1 is rigid contact, meaning we've assumed both objects are perfectly rigid, two like steel objects, colliding like this, right? Even harder than steel, right? Because steel would bounce a little bit, right? So the way that Fn is defined in the perfectly rigid case, Fn is the smallest force that resists penetration. It's the principle of least action if you want the variational version. Right, so this represents a constraint, and the forces of constraint in the principle of least action, which is a mechanics principle, are that the constraint forces are the minimal forces they need to be in order to, they make the minimal change to the unconstrained motion as possible. Now, what does that force have to be? What is the minimal force at the moment of impact is the interesting case. Anybody know the answer? I don't even have to tell you what m is. You can tell me the answer. At the moment of impact, Fn has to be infinite. Okay? Why? So if I were to plot as a function of t, let's say z dot. Let me just simulate for it. I'm going to a version of this of my plot here. So z dot is just going to increase. It's going to get more and more negative until the moment of collision. This is the and then in the perfect rigid model, z dot is going to suddenly be 0. Okay, so in an impulse, I went from having a negative velocity to having a zero velocity. And that requires an impulsive force. A delta function in force, okay? It has finite work, but over an infinitely small interval, so it's actually a delta function. Yes?
If you have a discrete time interval in between
yes.
simulations, is still okay?
Good. That's exactly the question. So this is in the perfectly continuous time case. And the question was, what happens if I now do my Euler integration? If I only ask that the penetration is satisfied at the finite time steps of my integration, which is all I tend to ask, then yes, you can have a finite force that resists and gets you perfectly back. Okay, so I was going to say that later, but I'll say that now. That's good. Let me introduce one bit of notation to say that carefully. So there's one other quantity that we're going to use generally here, which is the sign distance function. This is just the sign distance function we used in perception, right? This is the distance between the object and the other object that I'm trying to collide. Right, so this is the smallest force that resists penetration. Resisting penetration means that phi of q stays greater than or equal to 0. Okay. Yeah, and I think I guess I don't need it. Yeah. So for Euler integration, if we only require phi q at certain n to be greater than or equal to 0, right, at discrete times, then Fn can be finite. It's a little unfortunate. There's two n's there. Yeah, and in that case, it's still, we think of it as an impulsive force integrated over some finite time, so it has a finite magnitude. Is that clear? Yeah? How about yes? Good. Most of you aren't giving me any thumbs, but that's okay. I know it's a little strange. Okay, so, but this notion of rigid-on-rigid contact, which most of our mechanics is rigid body mechanics, leads to this seeming problem where I need instantaneous forces at collision, which makes it hard to simulate accurately. You could, if you want to simulate in as accurately as possible in continuous time, you actually have to do event detection, and you have to handle that collision event explicitly, and then continue integrating. If you make a discrete time approximation, then we're going to play different tricks. So let's just, before we move on to those time steppers, let me also say option 2 here is to think about soft contact. So now, when the ball is on the ground here, I'm actually going to, let me draw it even a little bit in penetration here. I'll make it instead a spring law that governs, I can make it bigger. You guys are far away. I've got a ball that's way under the ground, right? And let me put a spring that's trying to define my normal force. That would be an alternative, and I can do a spring damper. In fact, that's more practical to do a spring damper. And in fact, another good way to define the normal force here would be to say it's 0 if phi q is greater than 0, and it's negative phi q times k if phi q less than or equal to 0. And then we could add damping in too, for instance. This is actually, I would say, a better model of what really happens in the world than the rigid objects. No objects are technically rigid. But the stiffness of real collisions, because to simulate accurate things that don't penetrate much, like imperceptibly, right? When my foot's hitting the ground, there's a small deformation of my skin, right? But not a big deformation, which means in order to model that accurately, I have to choose K to be very big. And this is the tension, right? So now I can add stiffness in my contact model, but it means I have to simulate slowly, right? Even worse, the simulation is changing, the stiffness of the simulation in some sense is changing as a function of the configuration. So in my plot, it's hard to pick one time step that will work in all of the regions because the stiffness values are different in different regions. If I have two objects, if I get an object jammed between multiple objects, that's a different configuration. It's much harder to pick a single H that works for all the possible derivatives you're going to get across the states. Okay, so in practice, you'll pick K enough to visually be satisfying. You won't see, when we were first debugging Atlas, we would have Atlas fall a meter into the ground just to make sure that we got the time steps right and stuff like this, and then we would slowly tune that up. Okay, and then I should have said, but when I make H small, it takes longer to simulate, right? If I wanted to simulate for 5 seconds and my time step is small, it's going to take a long time to simulate. So this is the tension. How accurate do you want your physics to be? How large do you want K to be versus how fast do you want to simulate? Sorry.
My question was answered.
Okay, good. Is that clear? The basic story? Okay, so let's think now about friction. We've only talked about vertical force so far where vertical is always defined in this frame as the direction, the gradient of the sign distance function. So I'll say that more carefully, but in the ball falling from the sky, the normal force is always vertical. But for any two objects as they're coming together, the normal direction is it's the direction of closest distance, minimal distance. Okay, that's the generalization. Let's think about what friction looks like. In the simple case, let me now throw a ball sideways at the ground, okay? And when I get to the ground, I'm going to have, it's not my blue again, darn it. It's blue, I always break blue, yeah. You guys are not going to be able to see blue. Okay. That's my normal force, and I'm going to call this my tangential force here, okay? We came up with two ways to possibly define a normal force. Loads of details behind them, but the general idea is either the whatever force is required to completely resist penetration or a spring force to go like this. But we haven't said anything about slowing me down if I'm sliding along the ground. Okay, and the rigid approximation of friction is most famously Coulomb friction. Which says, again, it's a dissipation law, which says that my frictional force, my tangential force, is less than or equal to some coefficient of friction times my normal force. And inside that limit, then it's going to be the smallest force that resists sliding. Okay? And then once you're sliding, so this is sticking, and then once you're sliding, when you have a velocity at the interface that's greater than 0, then it's the maximal dissipation. It's the force that has magnitude mu Fn that dissipates the most energy. That just tells me what direction the force should be applied. The magnitude is going to be based on my normal force, and the direction is whatever direction would slow me down the most. Okay, this is kind of a strange thing, but the Coulomb friction law just says that if my object if I have a larger normal force, if I push down harder on my object, then it's going to resist, it's going to provide more friction, and it's proportionally more, and that I can summarize that friction interaction with this a single coefficient. Okay? In 2D, what does this look like? This is saying, I say it's greater than, I've got an absolute value of the normal force is proportional to the absolute value of the tangential force is proportional to my normal force. That means as my normal force grows, I can get more tangential force. And the way that we draw this, you could draw this as the admissible frictions here live in a cone. Right? As the normal force increases, then I can have larger tangential forces. Anything inside this region here. And this is called the friction cone. This definition still works in 3D. The friction cone now becomes an ice cream cone in 3D. It still describes a limit on the total amount of frictional force based on the normal force. Okay, so what happens here then? So when I said these things quickly, it's the smallest force that resists sliding, and then it's the maximal dissipation. So if you think about a simple case, for instance, of my ball, or let me make it a box so we don't think about the rolling version of it, okay, on an inclined plane. Then I'll have normal forces that live inside some friction cone. I'll summarize the contact at these 2 points for now. I can say there's little points of contact here, and the rest is suspended a little bit. Okay, so I'm allowed to have any force inside the friction cone. So what happens now? If I have mg pulling me down like this, and I have a frictional force that has to live inside this cone, right? That's trying to push up, and it's going to pick the maximal direction it can pick up. My artwork, I think actually I had forgotten to make this carefully, but I did make both of those red lines are consistently slanted. So given this beautiful rendition here, there is no force that can be applied at these points that would perfectly resist gravity. So this object's going to slide. If my if my mu was larger, my friction cone could increase. Do you see the geometric picture I'm trying to say? In order to get force balance, I would need a force of friction that's perfectly resisting gravity. Since this is outside my friction cone in that picture, that means that thing's going to slide. If I were to increase the friction cone by increasing mu, then I could get inside that. Or if I were to decrease the ramp, I could get inside that. Okay, but there's actually a beautiful geometric version of friction in that picture. Okay, ask some questions. Is this landing? Is this a useful level of detail? No? That's fine, yeah.
So basically it's because we want a force that opposes gravity.
Yes.
It's gotta be like perpendicular, like straight.
Yes.
But that's outside of the friction cone.
Exactly. So if I were to make a free body diagram, which I'm doing here, right, and I said I wanted the forces to balance, then in order for the forces to balance, the forces of contact would have to be able to be equal and opposite to the force of gravity. And because that is not an acceptable friction force, that means that it would slide. And in fact, the friction force you would get would be on this line, resisting as much as possible. That's the maximal dissipation idea. Resisting as much as possible, but ultimately still not stopping it from sliding. What else can I say to help? The friction cone idea is going to come up over and over again. You can't talk about manipulation without saying friction cone. So you don't have to understand all the details about it, but the concept of a friction cone is essential. Yes?
So do you want it to be inside the cone or outside?
The forces will always be inside the cone. That's the rule. And if I want this brick to stay still, then I would want the friction cone to have a force inside it that could resist that gravity. Yeah?
How did you determine, is this like arbitrary the way you drew the cone, or is it based off of like how the boxes lined up to the slant?
Good question. So the normal is defined. It turns out in the general case, it's defined by the direction in which the distance is smallest. In this picture, it's totally reasonable. I'm going to use the same color as here, is to say that the normal Fn was here. The tangent is a coordinate system that is on the surface. Yeah? When it's a two-dimensional surface, we have to pick a coordinate system for those tangents. And so therefore, the tangent in red is in this direction. It's normal. So that's what defined the geometry of that cone. The angle there is given by the coefficient of friction. I have a picture, actually, of the coordinate systems somewhere here. Okay, so in general, I have two general objects. I define the sign distance between those objects with this. The normal is always the direction of that sign distance, the gradient of the sign distance, it turns out. And the tangent is some choice like this. I tried to do a 3D picture. I hope that is sort of clear. You could pick any coordinate system on that surface, and then you'll design a cone, so it would look like an ice cream cone with the normal in the middle of the cone. Sliding friction's cool too, but I'm not sure if you have the appetite. Yeah.
How is the top of the cone closed? Is it a straight line or is it an arc?
So there's actually no top. So this law of friction, which is not a great law, honestly. It's the best we've got, but it has problems. I'll tell you the problem in a second here. But this says if you give me more normal force, I'll give you more friction. There's no limit. Yeah. Okay, here's a reason why it's bad. And this is why rigid contact is actually bad. Here's a thought experiment. So imagine I have a table with 4 legs. Okay? And all I know, all of the equations of motion would tell me is that if I walk up to a table that's standing still, then the normal forces must be sufficient to balance the force of gravity. So I know that there's a sum of normal forces that cancels gravity. Even more, I actually know that those forces have to resist the torque, any torques due to gravity. But I've got 4 feet, and I could produce the necessary torque with with only 3 feet. That means that the rules of mechanics don't actually tell me how much normal force is in each feet. It's like just a failing of our rules of rigid mechanics. Okay, so I could take some normal force over here and put it over here and still get a valid solution to the equations. Everything I've said here does not completely define what Fn is. Here's the problem now. So if you go to push the table, some of those feet might be in sticking, some of them might be in sliding. Depending on the normal force, you don't know what the friction force is. So the rules of rigid body mechanics will not tell me if the table goes straight or turns or left or right. All of them are possible solutions given the governing equations. They do not give me a unique solution to the differential equations I generate. That seems totally embarrassing, right? We have like so much smarts in mechanics, but we can't tell you which way the table's going to go. We would need a like atom level simulation of the differences of the actual contacts or whatever we need more than a point model of contact at each feet to resolve that ambiguity. I can write down a perfectly reasonable set of equations and it has non-unique solutions.
You said that the more force you give, the higher friction.
Yes.
I have like a billiard table with a billiard ball in it, and I start to press on a billiard ball.
Yep.
It's quite probable that it actually kind of slides away, right?
That's a different thing. Well, first of all, that's probably not good for your felt table, right? But like if my kids were doing that, I would yell at them. You're saying you push down and then it squirts out. Yeah? I think if you push down perfectly with absolute normal force, it wouldn't squirt out. You're putting a large force and you're accidentally putting a little bit on the side, and it'll go out. Yeah.
In that box diagram, if we put oil on that
Yep.
slope, would the cones change at all? Or
Yes, that's exactly, if I were to change the slipperiness, that is this coefficient of friction, the cones will come in and I will more likely slide. It's exactly the right intuition. Now, the interesting thing is that the coefficient of friction is really a property of the interaction between the two types of materials. So you can't say, this mustard bottle has coefficient of friction 3. It's when the mustard pairs with the steel table, it has a certain coefficient. It's in contact pairs, right? So it's a little annoying to specify, and people typically specify individual numbers for individual ones and come up with a hacky way to combine them in the simulator. Yes?
You're not considering contact area, right?
I am going to, not yet. But this is exactly right. So I summarized, that's why you heard me hem and haw about, okay, I just drew the forces there, but really there should be forces distributed potentially across that entire thing. But most simulators don't do that. So let's actually talk about that. So sliding friction is awesome, but I'm going to skip it. The basic, yeah, I mean, there's a different, the rules of governing what force you'll get when you do start sliding have similar rules. Typically, it's almost exactly the same with maximal dissipation, but most of the time people will say that your mu decreases once you start sliding. You'll have a different coefficient of sliding friction than static friction. So just if you see mu static or mu dynamic, that just means once you start moving, we have a different coefficient of friction. And that is, it shouldn't be that way, right? That's just like our equations aren't quite right, and we're going to cover it up by saying there's two numbers there, and they discontinuously interact. It's just weird. But this is our best rigid approximation. Okay, so now I think you appreciate a little bit more this notion of contact forces, how they need to be big, potentially. So for instance, this was back in the day when we were competing to win Atlas, and this was in Gazebo, right? And we didn't get to pick the parameters of the simulator, right? And it was really annoying to walk over the rough terrain because it would go like this, right? So one of two things should have happened at this point. If we had control of the simulator, we would have changed the stiffness of the ground down and admitted that it would sink in a little bit, or we would have turned the time step down, right? When you start seeing artifacts like that, that means you're getting into the regime where your integrator is not accurately tracking. There's a few other ways that you could get that artifact, and I'll tell you, but that's getting into the regime where your integrator is not tracking the true dynamics, and your first instinct should be to turn the time step down. Your second instinct should be to start looking for where the stiffness in your differential equation is coming from. Ironically, in the first demo, the Iwa moving around and picking up the block, I had to pick a certain time step, right? And I wanted it to run well in deep node and all these things. The place where the stiffness comes from, I think you'll never guess. There's just a Iwa moving around with a little red block. Any guess? What's the stiff part of the differential equation in that system? I've set you up to say it's the red block. It's not the red block. It's the fingers. It turns out the way that we simulate the WSG, I guess I did say it maybe a little bit, or that was excellent. But yeah, the WSG has a mechanical drive so that the two fingers are always equal and opposite magnitude. We simulate that with a stiff spring. Too stiff spring. Like it has to be stiff, but it's the thing that drives the bottleneck of my simulator. That's annoying. Okay, but at least I know it. I found it, and I know that if I want to make my simulator faster, I can change that number or handle that stiffness properly. Okay, let's think about the question of surfaces, right? So we had a question now that why did I draw two arrows when I really should be thinking about integrating over the surface? It's a pretty subtle thing. So most simulators think about force vectors applied at points. That's the natural thing to think about when you're writing a dynamics engine. But it gets subtle fast. So let's just think about box-on-box contact. That's what we saw when I dropped a bunch of red boxes out of the sky, right? So let's say I've got one box and I've got another box here, okay? Box 1 and box 2. Where do I draw the contact forces? My normal forces, right? I drew them here and here to make my free body diagram work, but that was a little arbitrary. You might think if you're writing the simulator that you'd think, oh, I'll just pick the corners. But that's not robust enough to handle all the cases, right? So where are you going to pick them if you find yourself in a situation where your box is hanging off the end, right? The points of maybe I need to somehow pick here and pick here, for instance, would be a reasonable choice. But there's another, there's other cases too. So because the integration time step isn't perfect, and I might not simulate the equations perfectly, I might find myself with my block like this. My integration wasn't perfect, so my geometries are overlapping a little bit. Now where do you draw the contact forces, right? It's not super clear, right? Maybe you pick here, maybe you pick here. Writing an algorithm that picks those forces consistently is hard, maybe impossible, I don't know. I think it has never been done. And this is another big reason why simulators of contact become unstable. Is you'll be simulating along, you'll take steps of the integration, and it will quickly change its mind about where the forces should be applied, and then all of a sudden something will explode. Okay? That could be what was happening here too, was that it could be slightly changing its mind about where the forces should be applied. So so here's a reasonable candidate, right? So let's say I've got two boxes that are in penetration. I think a natural algorithm that I would try to write would say I'm going to pick the point of maximal penetration, and then I'm going to take the closest exit from that maximal penetration, and I'm going to apply a force like that. Okay, so that's a pretty good algorithm. Yeah, but if I start looking at the way that force gets applied as I move the objects through, there's a problem, which is that the location of the force changes discontinuously as I move across that corner. So in particular, this notion of penetration distance and closest exit has the property that if I'm going in and I cross this corner, a force that was previously pushing me in this direction, my normal force, all of a sudden tried to decide me push up in this direction. Since I'm into penetration, it could be a large force that suddenly changed direction. This is another big source of stiffness or instability in the differential equations, in the contact equations. Okay, take a quick stretch, and then I'll tell you how to solve that problem. My blue chalk. Okay, I'm going to solve it because we only have a little bit of time left. So I think this really is a big source of errors in a lot of simulations. I think the answer in some sense was in your question. Why not integrate over the surface, right? The answer has just been it's computationally expensive and hard to do that computational geometry. But one of the things that has made the simulation engine in Drake much more robust now is by we're doing that extra work to integrate over the surface. So, a first trick, which actually we use a lot, is to just, and you could put this in any simulator, you can certainly put it in Drake. We often actually put extra contact geometries down. So for that red brick to fall and land in the piles and be accurate in all the different cases, if you visualize the collision geometry instead of the visual geometry, you'll actually see that the red box has a little box just partly inset from the original box, and then there's 0 radius spheres at all of the corners. Why? I'm telling the simulator, do your best in all these hard places to pick one point to summarize the force, but go ahead and put an extra point at the corners. Always do that. I'm saying there's an extra, we get one contact force per collision geometry pair. So by having extra points declared to the side, I'm just saying always pick the corners and then do your best on the interior. When we're simulating with point contact, that actually works surprisingly well, even in these sort of cases like the bricks falling down like this. If you watch carefully, this is actually only simulating with point contact. And I had to convince myself, like every one of those cases is actually resisting penetration because some corner is hitting that slightly inset box, right? Or the points on points. So it's a very good heuristic that makes these things work pretty well. Even if like gripper's picking up the box in the middle, it's all, that has worked very well. So if you just want to use a point contact based simulator better, then you can help by just making the collision geometry a little bit more friendly. Okay, but you can also do this harder thing of trying to do the surface integrals. How does that work? Okay, so this is called, in Drake, it's called hydroelastic contact. So it turns out the rules of physics across a surface in 3D of arbitrary geometry, they're not in a textbook. We had to invent some. That sounds bad. But we took our best extension of the existing laws of physics across a surface, and we applied them in this way. But it required first a bunch of computational geometry, which you take meshes intersecting with other meshes, and you compute volumetric meshes on the fly of the intersection. And then you try to take a surface inside that mesh, which summarizes the collision boundary, and you take an integral across that surface mesh. And you apply forces in a proportion across that whole surface integral. And that has made a huge difference in the way that we do simulation. You get these beautiful simulations that if you turn on all of the hydroelastic visualization, you'll see the rich contact geometry moving around. If you take the box-on-box collision, right, where it was changing discontinuously before, now we get beautiful, smooth changing in contact forces. Just to show the before and after here, right? That is a solution. It's an expensive solution to the problem, but that is a robust solution to the problem. Okay? There's a lot of computational geometry work behind that. And I want to be clear. So the model that we have going on here now is actually, in most of the cases, when I say it's soft on soft, for instance, that would be the spring-like model. So we have a stiffness. In these hydroelastic simulations, the object is not deforming. You can do fully deformable simulation too. This is a nearly rigid simulation. We're allowing penetration. So the contact geometry doesn't change, but on every instant we're allowing the penetration and we're computing an integral over the penetration to produce the force. So this is good for soft simulation in the low deformation mode. If you can say my geometry is roughly not changing, but I want it to be squishy a little bit, this is a good model for that, right? Or for a nearly rigid, if I turn K up on my stiffness, I can simulate pretty nearly rigid things with this, okay? It's not going to simulate a plush toy. If you want to pick up a plush toy and shake it around, or a rope or cloth, this is not the right model for that. That's what it means when I said state space for simulation and planning is the original rigid body state. It's not adding state to track the shape of the surface.
What does it do with friction?
Friction in hydroelastic, again, is, it's applied in a similar way. Sliding friction is even more subtle, but it required taking our best approximation of Coulomb friction on that surface, right? So it's in the paper. There's a lot of details, but it's almost Coulomb friction-y. Yeah. So it's more expensive than point contact, but less expensive than finite element, for instance. So you get these great simulations then if you watch the hand pick up the mug and you turn off the hand visualization and just show the hydroelastic regions. This is what turned it into a really robust simulation. This is one of the things, yeah? The other thing is a really good contact solver, so that we're not doing Euler integration. We're actually doing a much more advanced integration scheme inside Drake. The demo reels from the teams that are working on this are hilarious. They always just have random objects falling, and they always look beautiful and are doing more advanced things. But this week it was green peppers falling out of the sky, and this is now a green pepper in a bowl that almost falls off a table, but not, right? And the contact forces are being visualized. What's really amazing is if you watch the contact surface changing even between the bowl and the table. It's the little lip of the bowl, right? And that's so subtle to get that right. And if you want to measure the happiness of a dynamics expert, the measure is how smooth are those contact forces moving, right? There's some really fun situations. I think I've got a Lego example here somewhere. Yeah, we put Legos on, right? We're mating Legos. And the contact forces came out like this and were just like rock solid. And I think that was, ecstasy for the dynamics team. That was like, did you see what our contact force engine just did? Because normally it'd be like ping, 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 like this, right? In a lot of simulators will use this blocks falling from the sky as kind of a demo reel, right, of very advanced simulations. But it's a kind of a trick, right? Because you can't look at that and judge if it's physically accurate or not. In practice, if you were to zoom in, you'd see objects intersecting all the time, because what they do when they're simulating that is they say, I've got like 10,000 contacts happening. I'm going to pick 10. I'll make those work this time step, and then the next time step, I'll pick another 10. And that 10 is a magic number, right? And in net, it kind of looks like things fall and separate, and that's all good. But it's not very accurate. And the contact forces, like you'd see, would go beep, 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 all over the place, and they'd be missing in some places or whatever. So this is the real test is if you can visualize the contact forces and they are just sitting rock steady, then you've got a strong numerical recipe behind it. Let me ask, yeah.
For the hydroelastic contact surfaces, why is it important that we allow penetration again?
So, okay, so there's a multi-level response. So the question was, why is it important that we allow penetration? So fundamentally, if we think about a spring model, then there's no contact force until penetration. So the first choice is to do that. The alternative to a spring model is to handle the impulsive forces and try to obey those constraints exactly. There is a mode you can try to put one soft thing in with another hard object in hydroelastic that does some of this work. But right now, in the simplest version of the model, forces are only defined once you're in penetration. That's when you have a surface to work with. Mm-hmm. Yes?
You say slower, more expensive than the point contact, like for the mug with the hand. Like
Yep.
How long does that take?
Yeah. I mean, we always aim for real-time simulation. What's that?
Still real time.
It depends on which simulation, and it depends on the number of the mesh tessellation of the. So you have to take your surface mesh and make it a tet mesh, and the number of finite elements in your tet mesh will be the computational costs. So the reason it is not on by default in Drake is because it's slower, but it's actionable. We use it. We choose to turn it on often in our manipulation workflows. Yeah. Yes.
So using FEM is like hard to make it real time, or is also possible?
Right. So the question is, so what about finite element models, FEM? So let's just mention deformable simulation for a second here. So if I wanted to simulate a plush toy or something like this, then I might use a finite element model. Which is FEM, okay, which roughly says I'm gonna model my my Stanford bunny, plush Stanford bunny, with a bunch of springs and spring masses across the surface of the object, and allow them to compress and shrink and possibly change their relative location because the thing's deformable. FEM is just a computationally optimized version of that to some extent. So the question was, can we make finite element real time? I think people definitely have and can. GPU is a big accelerator for FEM type models, where contact is actually not is not optimized well by GPU because it's very branchy in the sense of you take a different path through the code, whether you're making contact between object 1 and object 3 or not, and that branches so much that the GPU isn't a huge accelerator. But for finite element, where you have a whole mesh and you know things are going to be, there's no branching on that particular mesh, then you put it on a finite element and people have very performant simulations. So there's an NVIDIA simulation of a fingertip with a soft finger that's running at real-time rates. Yes?
It's also for FEMs, so I guess it's not allow penetration in simulation.
No, okay, then there's a question of how does the finite element get connected with contact forces? And I think you can use all the same, if you treat each of your methods as, each of your elements as either rigid or soft, allowing penetration or not, I think all of those things can be handled, the same connections. Now, Drake has FEM also. It's not on by default either, but we do have a finite element method that's not GPU accelerated yet because it's very hard to release open source code that will work on everybody's GPU. But that's coming. And there's one other one I'll mention, but there's a question first.
So just to kind of summarize in my head, so you allow penetration to have the right normalized forces, but what happens if you have deformation on your blocks? Because then you don't have like that guarantee of like normalized forces, which you basically compute by like having penetration or deformation, not penetration.
Yes.
Then like it shifts again, right?
So this is a great question. So the recipe of trying to summarize a whole body when you're in penetration with a single force is difficult with a spring force. But if I'm willing to take forces everywhere, then the question is resolved again. So it's not just a single normal force that's being applied. You could summarize the total forces by putting a point somewhere. They're mathematically equivalent, but the way it's being computed is by taking an integral over the surface of contact. And so that ambiguity disappears. The other, so finite elements are good for I've never actually seen anybody shake a Stanford bunny, but I'm sure there's a paper out there that does that. But let's say I wanted a plush toy or something large and soft. When you get to like cloth simulation, that's an extra level of complexity because you have to worry a lot about thin objects. You can have piercing phenomenon. So if you take slightly too big of a time step, you're on the other side of, part of your object is on the other side of the object. And then, so you just have to deal with sort of these breakthrough events. But you can do that, again, with a finite element method, for instance, and extra work. But I would say, I don't claim the Drake can support cloth yet. That'll be a future work. The other one that a lot of people are interested in and have been working with is MPM, material point methods. Particle type simulations. So if you've seen NVIDIA Flex, for instance, or if you've seen like these particle simulations where you have something that could be a fluid, it could turn into a rigid, it can be something in between. This is doing like not quite the atom level, but like big molecule kind of level simulation of these objects. And on the GPU, it can be made surprisingly performant. You tend to give up a lot in terms of if you tried to simulate a rigid thing with an MPM model, you would find big gaps in the modeling. But for fluids and other things, again, if you were to compare it to Navier-Stokes, you'd probably find big gaps. But in terms of like, if I just want to see a robot crack an egg and see what that looks like, then I think it's the way that people have been trending. Yes?
I have some questions about multi-vortex, more than two-body dynamics.
Yes?
So it's like from the method we just learned, we can calculate the force between two objects.
Good.
So when one object is in contact with multiple objects,
Yep.
assuming like other bodies are also in contact with other objects. Right?
Yes.
Do we just solve a huge equation to get its next state? Or is it like iterate through everyone, assuming others are static?
It's a beautiful question. So yeah, the question, that's why I gave these optimization principles. They give trivial answers so let me repeat the question, sorry, which was, I've only said anything about two objects colliding, but I can have cases where, I've got a bunch of objects colliding, like in the blocks falling, for instance. So then how do these forces get resolved in that? So in the in the penetration with springs, it's clear. The interesting part is when I'm doing rigid contact, let's say, and I'm trying to avoid penetration in a multi-object setting, then you actually, you resolve these forces of smallest force that resists sliding and maximum dissipation in the multi-body equations with all of them adding constraints, and you solve an optimization problem in every time step to resolve the forces. These are the time-stepping simulators. If you've heard of linear complementarity problems, LCP, that is a way to solve this problem. It's falling out of favor because it's a bad numerical problem, but yes, we solve an optimization problem on every time step in order to figure out the forces in the general case. Great question. Okay, so your wizardry level of using, even just being a user of context simulation, I hope got up a little bit. You saw a little bit of what's going on behind the scenes. But if you take away one thing, if you see your feet shaking or objects, whatever, the first thing you do is you turn down the time step and make sure that phenomenon goes away. You should always be able to take that phenomenon away by making the time step small enough. It just might be painfully slow to simulate. But then what you do is you find the source of stiffness in your equations, figure out why the gripper was tuned with too high of a gain. It might be your controller. Oftentimes a controller will add stiffness, or it might be some contact parameter. Resolve that stiffness and then crank your simulation back up to get fast simulation. Okay, and what makes a fast simulator is really how big can you make H. There's a little bit about how much you've optimized your multi-body code, a little bit, but the dominant factor is how big of a time step can you take, and that's a property of your integrator and your equations of motion. Good. Okay, I'll see you Thursday.